Okay, so when we are matching, our first one has a power of 2, right? That was kind of nice because there's only one graph that looks like it has a power of 2. Which one is it? It is C. It's my only quadratic, right? So we know 1 matches up with C. Okay. My power of 3, there are 3 of them, right? And they all have the same end behavior. But what is different about them? Different x-intercepts. Is that what you're going to say? Sorry, I didn't see your hand. They have different x-intercepts, right? Except for, let's see, what is it? No, yeah, they are all different x-intercepts. So this is when our trusty-dusty calculator comes on in. Which one did you match up with F? I mean, dang it. What did you match up with number 2? F, you're welcome. So when you type that in on either graphing calculator or Desmos, because it does say use technology. So I did want you to do that. Use technology to match. Okay. You look at the x-intercepts and our graph F matches the function for number 2. All right. How about number 3? Which one went with number 3? E went with number 3. Good. And then what went with number 4? A went with number 4. Good. So the only difference between those 3, well, we had A and E both had a y-intercept of 0, right? F had a y-intercept of, looks like 2. Okay, so that kind of helps you with finding your F, matching up with 2, with the plus 2 on the end. That's still your y-intercepts. That's something you could have used to help you with that one. And then A and E, again, calculators help you out. Okay, my last 2 are both quartics, so they have that W shape. So we're looking at either D or B. Again, what's their difference? Their x-intercepts and their y-intercepts. Okay. B also cuts through the origin. D does not. Which one did you pair with function 5? D, which leaves us with B for number 6. Yes, no, maybe so. Yeah. So Desmos is great, but you do need the Algebra 2 skills of being able to factor and solve for x on your own. Okay? So I do have to make sure that you can do that. Desmos is great to check, but you're going to have to show me by hand. All right? So what we're going to go through today is some special factoring tools to do it. Because if I give you a function that's a power of 4 or power of 3, okay, we're going to be able to use factoring and what we did with dividing to help find all of our pieces, okay? We have lots of factoring methods for degrees of 2. There's basic, there's slip and slide, there's complete the square, quadratic formula, right? There's other methods for pieces that have a degree of 3 or degree of 4, okay? Some of those special cases, we have difference of 2 squares, sum of 2 squares, difference of 2 cubes, and sum of 2 cubes. Okay, so we have our squares. These both should look familiar. What special thing's happening? It's the same factor, but one's positive and one's negative. Starts with a C. Ends in conjugate. Conjugate. Okay, those are conjugates. It's the exact same thing. Remember, because that middle piece is missing. So if you have a squared minus b squared, that can simplify to a plus b and a minus b, right? If there was a sum of 2 squares, before you would have to say that it couldn't be factored. But now, because of i's, we know I can do the complex conjugates. So it becomes a plus bi and a minus bi. Okay, remember we did that working backwards to solve your quotients when we divided? Yeah, that was the complex conjugate theorem that we used. So it's just that backwards. Okay. Then we have difference of 2 cubes. Okay, difference in sum of 2 cubes. They both have a pattern. If you notice, they're both a and then a b and then a squared and then ab and then b squared, right? We see that they're the same. Difference is their signs. Okay, so I got something to help you to remember their signs. I have soap. Okay. Same, opposite. So same sign, it matches the original. Your next sign will always be opposite. Your last sign will always be positive. Okay, so you got soap. If it's a sum of two cubes, your first sign is the same. It's a plus b. Then it's a squared minus ab. That's the opposite. Your last sign is always positive. Okay, so a, b, a squared, ab, b squared. That pattern is always there. And then the signs come from what the original sign was. So our first two are conjugates. One's a real conjugate, one's a complex conjugate. Our last two with our cubes, we're going to use soap. Okay? So let's do some examples over here. I have a cubed minus 125. Which one of my special cases is that? It's a difference, right? We have a minus sign. Are those squares or are those cubes? They are cubes, okay? So in order for me to simplify it, looks like I need to know what a and b is. How do I figure out what is a and what is b? If a cubed is x cubed, then what's just a? X. If b cubed is 125, then what's just b? 5. Right? Because it's set up as a cubed minus b cubed. So that is x cubed minus 5 cubed. Does that make sense? Yes? Now that you know the a and b value, now we can set it up. So we're going to do a minus b because my first sign is the same. So x minus 5. And then our next set is a squared. So that's x squared. Opposite sign. A times b, a times b, so x times 5 is 5x. Our last one's always positive. B squared is 25. And that's it. And that's where you stop. All right, my second case. I see a plus, so it's going to be a sum of something. Is that sum of squares or sum of cubes? Sum of squares. So we're looking at this guy. So I need my complex conjugates. What's up?
For the x cubed minus 125, why would it be negative 5?
Because it's minus b cubed. So the minus is already just part of the equation. B itself is just 5. Okay. Yeah, all of these, the signs are not part of your actual a and b value. So a and b, b will always be a positive number. A could be negative, technically, put it out front. But since that's minus b, then you take b as it is. Then it becomes a plus b cubed, then you do the other equation. All right, so this is a squared plus b squared. So what is technically my a value? 5w. What is my b value? It's a 2. And since we're doing complex conjugates, I need to do plus 2i minus 2i. So a sum of squares results in a complex conjugates. All right, 8t cubed plus 27. What do we got? A sum of cubes. Yes? So now we're doing this guy down here. I need to know what is a and what is b. So if a cubed is 8t to the power of 3, then what was just a? A 2 and a t. Does that make sense? The cube root of 8t cubed is 2t. If b cubed is 27, take the cube root. What is the cube root of 27? 3. Oop, I was about to write 2. There we go, 3. All right. So we're going to have a plus b first because my sign is the same. So that becomes 2t plus 3. Next is a squared. Well, my a is 2t, right? What is 2t squared? What is 2 squared? 4. And then t squared is t. Yeah, you're good. Our next sign is opposite, so it's going to be a minus. Your middle piece is a times b. So that's 2t times 3, which is 6t. And then always positive. My last piece is b squared. So what is 3 squared? 9. Like that. There you go. All right, so these are special cases that will come and help us later. Questions, comments, concerns at this point? So sum and difference as squares and cubes is what that was about. All right, some polynomials with a degree greater than 2 can be factored completely using techniques you have previously learned. A factorable polynomial with integers coefficients is factored completely when it is written as a product of unfactorable polynomials with integer coefficients. Okay? So my first one here, I have x cubed minus 4x squared minus 5x. It's almost basic factoring, right? I have the 3 pieces. There's a 1 out front. It's almost there, except it's not a quadratic. Okay? Can I make it a quadratic? Yeah, because I can factor out what greatest common factor? An x. So when I factor out the x, it doesn't disappear. It just gets moved out front. So now it's x times negative 4x minus 5, like that. So x is a factor. X squared minus 4x minus 5 is a factor. Okay. Am I done factoring? No, we can factor what's in my parentheses right now. Now I can think to myself, okay, what multiplies to give me negative 5 but adds to give me negative 4? 1 minus 5. Do you all agree? Is 1 times negative 5 negative 5? Is 1 minus 5 negative 4? Yes. So x is still a factor. Now I have x plus 1 as a factor and x minus 5 as a factor. Have I factored this completely, or is there still more that I can do? That is done. The big clue there is that they all have a power of 1. Also, all of my x's will just have a power of 1. Will that always happen? No. But if you get to that point, you are done. You can't do anything else. Okay. Yeah, but it has to be an integer. So gotta watch out. Sorry. Here we go, part B. 5z to the power of 4 plus 30z to the power of 3 plus 45z squared. Is there a greatest common factor? Yes. What is it? 5z squared. I can divide that out of every single piece. 5 divided by 5 is just 1. What is z to the 4th divided by z squared? Z squared. Come on. There we go. What is 30 divided by 5? 6. Z cubed divided by z squared? Just z. 45 divided by 5? 9. Z squared divided by z squared? Mm-hmm. Okay, so 5z squared is a factor. Z squared plus 6Z plus 9 is a factor. Am I done factoring? No, I can do more with what's in there. Does anything multiply to give me 9 and add to give me 6? 3 and 3. So when this happens, we have two of the same thing, right? So you're going to put it Z plus 3 squared. So that shows you your factored form. It also shows that I have two x-intercepts if I were to graph this. Something else to point out. So my degree here, z squared and a squared, what's 2 plus 2? Isn't that what we're off with? Yeah? Over here, x1, x1, x1. That gives me x3, right? What did I start off with? X3. So make sure that always matches. If that doesn't match, something went wrong somewhere. Yeah. It should always match. Even here, 2, 1, 1, that's still 4, right? That's just not how we write our family answer. This is how we write our family answer. We good? So GCF and then basic factoring. On the back, we're going to remember how to factor by grouping. You want to remember this fun thing? Where you had 4 pieces? No? Has anyone seen factor by grouping before? Yes? Familiar? Sounds familiar? Okay. So factor by grouping happens when we have 4 terms. Okay? So what you're going to do is you're going to split it in half, find a greatest common factor from the first half and from the second half. The pieces that factor out get put together as a factor together. And you'll notice what is left over should be the same thing because that's the second factor. Okay? Let's put some numbers with this so you can see what I'm talking about. So z to the power of 3 plus 5z squared minus 4z minus 20. You have 4 pieces, cut it in half. Okay? Look at just the first two. Z cubed minus 5z squared. What can I factor out of just those first two pieces? A z squared, which leaves me with z plus 5. Okay. Look at this, the last two. Negative 4z minus 20. What can I factor out? Negative 4. And then what's left over? Z plus 5. Do you see the math magic? You see what happened? Okay. These factors are the same. That has to happen because that is one of my factors. Okay. That has to happen. And then my other pieces, the z squared minus 4, they're going to get put together to make your second factor. So we have z squared minus 4 and z plus 5. So there's that piece, and then that piece. This is where they go. I have factored by grouping. Am I done factoring this problem? No. A special case popped up. What do you see happening? I see a difference of squares. See that? X squared minus 4. So how does this guy split up? X plus 2. X minus 2. Oh, sorry, we're doing z's. Z plus 2, z minus 2, and then we have z plus 5. That is completely factored. So if you stopped right here, you wouldn't be wrong, but you would not be done, and you wouldn't get full credit. You got to make sure you keep going all the way down, if you can. All right, how about you try the next one? X to the power of 3 plus x to the power of 2 minus 16x minus 16. You try that one. All right, check with me. How'd you do? Yes? No? I'm getting blank stares. Are we okay? Yeah? Okay, so when you split it up, when you divide x squared out of the first two, you're left with x plus 1, because x squared divided by x squared, there's just a 1 there. Other side, they can both be divided by negative 16. Again, you have to get x plus 1 again. If you don't get the same thing, something went wrong somewhere, go back. Okay. And then again, you have a difference of squares. X squared minus 16 can then be factored again to be x plus 4x minus 4. Yeah? Okay. The next two, we're kind of putting all the stuff together. So we're looking for special cases. We're looking for GCS. We're looking for all the pieces, okay? So part A, there's only 2 pieces, right? So we're not going to do grouping. We can't do basic factoring, okay? But do I have a greatest common factor? Yes. What can I divide out of 36x to the 5th and negative 81x? A 9 and an x. Which leaves me with what left inside? Minus. There you go. Good. I have 2 pieces, so let's think. Is that a special case? Is that a sum or a difference of squares or a sum or difference of cubes? It's one of them. It's a difference of squares. It's a difference of squares. 4 is a perfect square. 9 is a perfect square. Bonus information, every even exponent is a perfect square. You just cut it in half. Because 2 plus 2 is 4, right? 3 plus 3 is 6. 4 plus 4 is 8. Because when you multiply exponents, you add them together. So whenever you have an even exponent, that is a perfect square exponent. So to break this one apart, so what would be the square root of 4x to the 4th? 2x to the 2nd. Good. And what would be the square root of 9? 3. So we're going to do 2x squared plus 3 and 2x squared minus 3. Double check one more time. Neither one of those is the sum or difference of squares or cubes, so this one's done. If it had asked me to find the x-intercepts, that's when you would do one step further to make each piece equal to 0. So each factor, so 9x is a factor, 2x squared plus 3, 2x squared minus 3. You would make each piece equal to 0 and then solve for x. Okay. This problem has 5 x-intercepts. It is a lot of x-intercepts. Guess what? The next one has 8. I know. The next one has 8. So we'll talk about multiplicity later also. So like when an x value shows up twice, like if you have x equals 5, x equals 5, it's not going to cut through that spot anymore. It actually bounces off. It hits it and bounces away. So some of these have turns or curves happening within them because of multiplicities. So a power of 8 doesn't mean it cuts through 8 times. But we'll get to that later. For part B, though, with my power of 8, I have 3 pieces. I would love to be able to basic factor if I can. But look for a GCF. Do I have one? Yes, I do. I can do a 3 and a P2. P squared. Good. 3P squared. Which leaves me with P to the power of 6. In the middle, we have 5P to the power of 3. And then we end this with the plus 6. All right. It's not. Sum of cubes only comes from 2 numbers. So this one is a trinomial. There are 3 pieces. Okay. So we still look for what multiplies to give you 6 and adds to give you 5. Think about that first. 2 and 3 multiplies to give you 6, adds to give you 5. Yeah. So we know there's going to be a 2 and a 3, right? But what's happening up front? I have a P to the power of 6. How could I split that in half? P3. Okay. If you were to actually multiply this out, you would have P3 plus 3P, which is still in my equation, right? You would end up doing P3 times P3, which is what gives you the P6. Okay. So again, even exponents can be split apart. As long as with trinomials, that thing in the middle is what it is cut in half. Okay. So if that was a 4 or a 2, then we couldn't have done what I just did. But 3 is half of 6. That's why I'm able to basic factor. All right. Is there any more that I can do? So those are perfect cubes, but 2 and 3 are not perfect cubes. So neither one of those is a sum of cubes. So we are done. All right. Ready to tie in yesterday and today into a word problem? Yeah. I love the enthusiasm. Let's do it. All right. Because the x-intercepts of a graph of a function are the zeros of the function, you can use the graph of a function to approximate its zeros. If k is a zero of a function of f, then x minus k is a factor of x, of f of x, and x minus k divides evenly into the function. So we can use polynomial division to check the approximated zeros. Okay, so looking at this is a function that represents the height in feet of a roller coaster after t seconds, where t is between 0 and 5. How long is the roller coaster under the ground? So we are looking specifically at this piece of my function, correct? Okay. So I know one of those x-intercepts is what? That's definitely a 2. But I don't know this. It's 4 point something, right? 4 point something. I don't know exactly what it is. Okay. So we're going to use what we know, because right now I can't factor this equation. Even grouping is not going to help me. Okay. I need to bring this degree down 1 so that way I can factor it. What did we do yesterday that brought our degree down every single time? Yeah, our synthetic division, right? Brought it down by a degree every time. Looking at my graph, I have an x-intercept of -1, +2, and then I don't know, okay? Use one of the ones that you know to reduce our equation down, okay? So would you like to use -1 or would you like to use 2? 2? All right, so we're going to put 2 in here. 3, 2, 1, none. All of my terms are represented. So bring in our coefficients. 4, -21, 9, and 34. Drop the 4 down. Multiply to get +8. So now we're going to add. What is that, 13? -13. Multiply to get -26. Add those together to get -17. Multiply to get -34. And we get 0. Did I just prove that +2 is an x-intercept? Yes, because my remainder was 0. Okay, so that has to happen. If you did not get a remainder of 0, you messed up, or it's not an x-intercept and you picked a wrong button, a wrong x-intercept value. So now I have a new equation. I have 4x squared minus 13x minus 17. We brought our degree down 1. That's the point, because now we can factor this. Okay? Ready to remember how to slip and slide? Because we have 3 pieces, right? Yes? My A value is a 4. It wasn't any of those special things that happened earlier. So we are going to move this guy to the end. So x squared minus 13x. What's 17 times 4? Was it 68? Yeah. So now we're looking for things that multiply to give you negative 68, but add to give you negative 13. 4, negative 17. Positive 4, negative 17. And then what do we have to do from each piece? Divide the 4 back out. Remember, you had to slip the 4. This step, you slide the 4. So remember, slide, divide. So this factor becomes x plus 1. But this factor becomes, what, 4x minus 17? Because your denominator gets promoted up. Because 4 over 17 didn't simplify. 17 over 4 didn't simplify. All right, so look right here. This gives me an x of negative 1. Oh, did I just prove the other one? Look, I've proved 2 and I've proved negative 1. I got that as one of my answers. That we should have expected that to happen. The other guy is going to give me the one that I don't know. So let's see here. Add 17 over. Divide by 4. We should get about 4.25 for this piece. So that's how we use synthetic division and our factoring to help me find x-intercepts that are not going to be whole numbers. Okay. Now, I have to answer the question. The question was, how long is the coaster underground? So I kind of marked it. I know it's in between 2 and 4.25 seconds. So how long is that? 2.25 seconds. The roller coaster is underground for 2.25 seconds. Okay, because we saw it was between 2 and 4.25. Yeah? You like it when it all comes together? I like it when it all comes together. I feel like it gives it meaning of why are we doing this?